Hello, Concrete Kitties. My name is Tyler Lay, and this is an exciting episode because I get to talk about air-entraining admixtures, my favorite admixture, and arguably, in my opinion, and actually most people's opinion, the most important admixture that we use inside of our concrete. Air-entraining admixtures, they're critical, and so critical that if you are in a freeze-thaw environment, if you're in a place where concrete gets wet and concrete freezes, you got to have them. If you don't have them, you won't have freeze-thaw durability. Okay? So they're essential if you're in these environments. What are they? They are anionic surfactants or soaps. Soaps. Yes, we add soap to concrete as we're making it. Yeah! Because we want to stabilize these small bubbles. You add the soap, it makes bubbles, and through the mixing process, you whip air, you trap air into the concrete, and you break and split those bubbles over and over and over and over and over again. And the air-entraining admixtures, they help stabilize the bubbles. And I'll explain what I mean by that. First, they are surfactants. What's a surfactant? Well, it's a special molecule that has a hydrophilic, what's that mean? Hydro means water. Philic means love. It loves water, a part that loves water. And then it's got a hydrophobic tail. That means it hates water. And these surfactants align themselves around the air-water interface, all right? And they help stabilize bubbles. They help make bubbles that stable or thermodynamically possible that wouldn't usually be there because we want a certain size bubble. We want small bubbles, not big bubbles. But there's another huge benefit of these surfactants. They actually attract cement grains. And these negative charges actually attract cement grains, and this helps hold the bubble in place. It helps keeping it from floating out of the concrete. Like if you ever go to the ocean and you see a wave come in and crash down on the surface, that wave traps air, right? And we see it come out as foam. Well, the same thing's happening when you make concrete, but those bubbles don't escape. They're held into the concrete by the air entrainer. Isn't that amazing? These surfactants, not only do they attract cement grains, and I'll show you that, I'll prove that to you coming up, but they also form this kind of shell material around the void that helps the bubbles from coalescing. And it also stops air from exchanging between the bubbles. So this shell is really, really important. I'm so excited to share this with you because this is work from my PhD. Yeah, I know it's super old, right? Nah, just kidding. I started out to try to prove or learn more about air-entrained concrete. And I started out using these bottles that were optically clear. You can see right through them. And then I filled these bottles full of air-entrained cement paste. I didn't fill them all the way up. I filled them up. And then I put the lid on them and turn them over on their side. Okay, just like that. And over time, the cement is going to go to the bottom and the water is going to go to the top. And this is called bleeding, right? We know this, okay? And that water, when it comes up to the top, it's going to bring with it air bubbles. And I'm going to be able to watch these air bubbles in the surface. And I'm going to use this stereo microscope, which is hooked up to a computer that I wrote a program to take pictures over time. And this was the very first video I ever made. Let's watch. So over time, not much is happening. Every second in this movie is about 5 minutes in real life. Okay? So it's kind of boring. And then, look at this. seems to be an impact on the bubble from below, this large bubble. There's a split. And watch, the bubble seems to be emerging from the inside of the shell. And watch, the bubble just takes over like the blob. Ah! I know. Pretty awesome video, right? Let's watch it again. I want you to keep your eyes down here. What happens is the cement paste is expanding because it's heating up while it hydrates. And as it expands, you'll see it impacts or pushes. And once it starts to push, watch, there'll be a crack that forms right in the surface of the bubble. And as it keeps expanding, it keeps forcing this bubble and crushing this bubble. The bubble doesn't bend like a basketball. It actually cracks on the outside. And watch, look at this. This inner thing emerges. Holy cow. And watch, when it goes to touch these other bubbles, they don't coalesce. They don't join to become larger bubbles. It pushes them. Watch. Push, 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 push. Shoves them out of the way. Pretty cool video, huh? Let's talk about what happened. That was air-entrained cement paste. The paste seems to rise up and push on this large bubble. And the diameters do not change over time. The diameters were pretty constant. I don't know if you noticed that or not, but the diameters didn't change until the bubble was pushed on. The bubble seems to have some kind of shell surrounding them, okay? And the bubbles, and because we saw it crack and this bubble emerge from the inside, and the bubbles don't coalesce. They just kind of push each other around. And that was air-entrained cement paste. I know, awesome, right? Now, I didn't want the paste to keep crushing my bubbles. So I had to modify my experimental setup. I had to use it now where my paste was below and my bubble was above, right? So the paste can rise up and down and it's never gonna touch my bubble. It's not gonna touch it. And let's just see what happens. These are non-air-entrained bubbles. And notice I have letters on several of these, okay? And I'm gonna show you a graph of how they change over time, but let's just watch. Whoop. Let's just watch. Now we can see over time, again, every second is 5 minutes, and the larger bubbles are getting larger, right? You see them? And these smaller bubbles, look at that one, get smaller. Look at that one over there. Look at that. What is going on? There's actually air interchange happening between the bubbles, okay? This is widely known in physics, okay? I've got different letters for the different sizes of bubbles, and we can see some of these bubbles got small, some of these bubbles stayed around for a while, then they got small, and some of these bubbles just kept getting larger and larger and larger. Remember, that is a non-air-entrained bubble system. Let's talk about what happened. The air voids were not affected by the paste, as in the paste didn't crush them, right? The bubbles appear to be transparent. Did you notice that? Let's go back and look. The bubbles are transparent. They don't quite have that shell around them. I'll talk more about that coming up. And the bubbles change in size with time, even though nothing is touching them. That is non-air-entrained bubbles. But let's go back. Let's look at air-entrained bubbles. Let's start this movie. Might as well let it go for a while, because it goes for hours and hours, and there's no change in the bubbles. It goes and goes and goes. It's the most boring movie I ever made. So we can see the bubbles look totally different. They're not changing in size. Nothing is changing. It's boring. That might be what you want if you're making concrete. You might want to make a bubble system and then have it stay there. So this was air-entrained paste, and the air voids were not affected by the paste. The paste didn't come up and crush them. The bubbles appear to be covered in a shell. Do you notice the difference? There's this shell around them. And the bubbles don't change size with time. Let's do another one. Now, in this system, I've actually pressurized the bubbles, then depressurized them really quickly. I used air pressure. And if you notice, there's a split in this large bubble. See this split right there? Okay. Let's watch what happens. So as we start the movie, if we watch, look at these smaller bubbles. They're changing in size. They're decreasing in size. You want to see that again? Let's watch it again. These bubbles were larger. Now let's watch. Let's keep an eye on them. As this one cracks and opens up, it's almost like an eyelid opening up. The bubble's going to get smaller. Watch. Yup. It shrinks in size. When this shell is broken, this air interchange can then begin to start to happen. Okay? So air-entrained paste that's been pressured, that's what we're looking at. The shell of the large air void's damaged, and the smaller ones probably are as well. We just can't see them. The smaller bubbles decrease in diameter, and the larger bubble increases in diameter and kind of opens up this shell around the outside. So it appears that the shell is created when an air entrainer is used. And the shell seems to be important in resisting the transfer of gas from the surrounding fluid. And if this shell becomes damaged, then it seems to be possible this transfer of gas can then start occurring again. Now let's talk about some properties of the bubble shells. We're going to talk about physical properties today, and we'll talk about transparency, adhesion, and this air void shell response to pressure, and then self-healing. Ha! Yeah, I know. Amazing, right? We can see these two air void systems. This is stuff I showed you before. They look different. They have different transparency. This one, we can't see through the bubble. We can see a shell or a texture on the outside. And this one, we can see right through it. Pretty crazy, right? So they just look different. Let's talk about adhesion of cement particles. Now, in this movie, every second is about 16 seconds, and I'm going to actually change my depth of focus. I'm going to start out looking at just the surface of the cement paste. And as you can see there are a couple bubbles that are just poking their head out of the surface. And what I'm going to do is I'm going to let the time go, and over time I'm going to change my focus, and I'm going to watch these bubbles emerge. Ha! Here they come. Here they come. Are you scared yet? Look at these bubbles. They've risen out of the cement paste. Let's watch that again. They rise out of the cement paste, and they're like the creature coming out of the blue lagoon, right? And they bring up with them a huge chunk of cement paste. Look at those divots they leave behind. Like if that was a golf divot, people would be mad, right? Look at that. That's a lot of adhesion. That's a lot of attraction between those cement grains and the surface of the bubble. Now let's talk about the air void shell response to pressure. Now different air entrainers behave differently. Let's show a Vinsol resin at first. And as you increase the pressure on the Vinsol resin, it gets smaller. And then as you start to decrease the pressure, they crack. And that's kind of what we showed you before. The bubble shell cracks, and you can see inside of it. Crazy, right? Now let's look at a different system, a synthetic air entraining agent, okay? Or a sodium olenate. When you increase the pressure, it doesn't just shrink like a normal bubble. It bends and twists and buckles, almost like a Walmart bag being squeezed. And then when you decrease the pressure, it comes back, and it's a pristine bubble. You can't see any damage in it at all. Now let's talk about self-healing. So this is a whole bunch of bubbles, and I was pressurizing them and depressurizing them over and over again. And we're going to focus on this bubble right here, okay? We're going to zoom in on it, and I'm going to watch the movie. I'm going to play the movie here. We'll play it through once, then I'll talk about it the second time because it's that amazing. Let's start it going here. And again, every second's about 5 minutes. And you can see the bubble shell's been cracked and it's kind of losing its shell, okay? And then over time, look closely. Check that out. Crack's going away. What happened? What happened? Well, let's do it again. Over time, bubbles cracked because I pressurized and depressurized it. It opens up and you can see the inner bubble. But over time, it seems to be the shell is reforming on the surface again and again and again. And it gets to a point where it zips itself back up. It heals itself. Isn't that amazing? That's just crazy, right? So in conclusion, we see bubbles that are air-entrained. They have a different transparency than non-air-entrained because they have a shell around them. These cement particles adhere to the outside of the bubbles. It's true. I've seen it. Different air-entraining agents respond differently to outside pressures, okay? And the bubble shell have been observed to repair themselves. Pretty crazy, right? Typically in concrete, we try to entrain about 4 to 8% air. Now, if you just make concrete without any air entrainer at all, it will still have air in it, about 1 to 2 usually, 1 to 2% by volume. But when we want about 4 to 8% air, and how much air do we need? It really depends on the bubble size distribution. And at 4 to 8%, there's anywhere between 10 to 15 billion with a B, air bubbles per cubic yard. And a truck of concrete holds about 10 cubic yards. That's 100 to 150 billion bubbles floating around in that concrete truck. That's the same thing in a cubic yard as 250 bottles of champagne. Oh, that's a lot of bubbly, right? That's amazing. But people love to ask this question. Is the volume of air enough to determine freeze-thaw durability? And I say no, it's not. That it's about the air void spacing. And I'll tell you about that. What do I mean by that? Well, I'm showing a picture here where I have an air void, and around it is paste. And these are these little bitty pores that are filled with liquid. And upon freezing, the water tries to expand. There's about a 9% volume change that tries to happen when water starts to freeze. And it freezes in these very, very small pores, okay? And it actually shoves water to the large bubbles. They actually travel to the large bubble. There's only a certain distance that this water can travel over. This is this water. I'm showing these arrows as water movement on freezing. And this moisture ends up entering the void and ends up forming ice crystals. People have imaged it. It's pretty cool. But there's only a certain region or zone that this water can travel over. And this is called the protected paste volume. And the volume around the air-entrained void is where freezing liquid can escape. So because of this, if we can make a small, well-distributed air void system, we're going to have much better protection. What do I mean by that? If I have these just a couple large bubbles, I'm only going to have a certain amount of protection. And if you notice, the same thickness of this protection is the same thickness over here because the protection zone doesn't have anything to do with the size of the bubble. The protection zone only has to do with the properties of the paste. So I get a lot more protection out of these small, well-distributed bubble system. Whole lot more of my paste is protected. How do we know what this is? How do we measure this? Well, the size and the spacing of the voids can be measured in the hardened concrete with something called the spacing factor that you get out of a hardened air void analysis. I'll tell you about that in just a second. But the spacing factor, if I have this idealized spacing of my bubbles, this is kind of like the longest distance that a water molecule would have to travel in this idealized spacing or system. And this diagonal distance would be the largest one, and this would be twice something called L bar, or the spacing factor. So how do we get that spacing factor? Well, we have to do a hardened air void analysis. We actually have to cut the concrete, polish it, and then we have to go over it in a systematic manner and count bubbles. The technique I'm going to talk about today is a linear traverse technique, where it goes over in a linear line, and every single time that line hits a bubble, you measure how much of the bubble that it cuts through. It's called a chord, okay? And we can make a plot of the chords on the x-axis versus the frequency, or how often they end up occurring. And these are the small voids over here, and these are the large voids over here. Now, their chords and voids are two different things, okay? But they're somewhat related to one another, So we would say the green one is what we want, and the blue one is not as much of what we want. The green one would have a low spacing factor, and the blue one would have a higher spacing factor.